Hi all. Today I'll talk about my work on the background of radio photons from primordial black holes. This work was done in collaboration with my PhD supervisor Girish Kulkarni. Let me start by first giving a motivation for this work. As you all know about the edges detection of the 21 centimeter signal in 2018, which was found to contain an absorption feature quite strong as compared to what the standard models would predict. In this figure, the black dashed line is the measurement by the edges collaboration, and a standard model prediction is shown by the red solid line. And clearly, you can see there is a significant mismatch between the two. A potential explanation of this discrepancy is an excess radio background. In general, the 21 centimeter signal is found to be proportional to the neutral hydrogen fraction and this factor 1 minus Tr by Tk. In this, Tr is the net background temperature against which we observe the 21 centimeter brightness. In standard calculations, this Tr is taken to be CMB, but in the presence of excess radio background, this would be CMB plus some excess radio background. In the presence of excess radio background, the new prediction for the 21 centimeter signal is shown by the blue curve in this figure, and now we can clearly see that the depth of the absorption and the theory are now in reasonable agreement. Let us now try to understand what this excess radio background is about. But I need not go into the details of this excess radio background as this forms the basis of this conference. But I'll just mention that the origin of this radio background is unknown, and we find that about 5% of this excess term accounts for the depth of the edge is 21 centimeter signal. There have been various exotic physics mechanisms that try to explain this kind of excess radio background. Some of them I have listed over here, but this list is not, of course, exhaustive one. For example, annihilating axion-like particles decaying into standard model photons could give rise to the excess radio background. Other possible explanation is resonant conversion of the dark photons into the standard model photons, and many more such mechanisms are there. In this work, we try to explain this excess radio background from the emission from the accreting primordial black holes. Primordial black holes are interesting dark matter candidates. They are formed much before the cosmic dawn due to the gravitational collapse of overdense regions. Uh, the parameter FEBH is the density of primordial black holes related to dark matter, and this figure shows a constraint on this parameter available at different masses. We are interested in masses of the order of 10 to the 8 solar mass in this that covers this range. For these type of primordial black holes, accretion becomes quite important. As we all know that accretion could give rise to strong relativistic jets, and the spectrum of these jets can in principle span a very broad range of frequencies, which also contain the radio band. So the idea is to estimate the radio band radio emission from these accreting primordial black holes, and the calculation is actually quite straightforward. Here I'll give a brief summary of my calculation. To start with, we begin with calculating the emissivity of the collective accreting primordial black holes, which in turn can be written once we know the number density of these primordial black holes and the luminosity for a single accreting primordial black hole. The number density, we assume that it's a monochromatic distribution of the primordial black holes, and we assume that the mass density of the primordial black hole is some fraction of the dark matter density, and that fraction is FeBH that I mentioned earlier. But the most challenging part of this calculation is the calculation of the luminosity Lr for a single accreting primordial black hole. There are mainly two aspects that are important for the evaluation of the Lr. We first need its magnitude. And secondly, we need its energy dependence or the frequency dependence. For the calculation of its magnitude, we know there are certain physical mechanisms available that through which we can estimate the magnitude. However, at very high redshifts, we are not certain about the mechanisms and we do not have the data. And for that reason, we use a more conservative approach and we use some kind of empirical relations. Those relations are known as the fundamental plane of black hole activity, and this is the relation that we use in our work. In this relation, Lx is the luminosity in the X-ray band, Le is the Eddington luminosity, and this relation is calibrated at a frequency of 1.4 gigahertz. So basically, we see that this relation connects the luminosity in the radio band to its luminosity in the X-ray band and indirectly with the mass of the primordial accreting black hole. The mass, by the way, enters the definition of Eddington luminosity Le. Secondly, we need the energy dependence of the this LR. For that, we assume that it's a power law and the index is minus 0.6. This is expected for a synchrotron emission mechanism for the relative jets, along with the first order Fermi acceleration in shocks. Finally, there are also two free parameters in our calculation, mainly F duty and lambda. F duty is the duty cycle, which is the probability for a black hole to be actively accreting at a particular time, and lambda is the Eddington ratio, which quantifies the ratio of the bolometric luminosity to the Eddington limit. Interesting about this number minus 0.6 is that if you convert the final dependence of this J with energy, we get a power law that is index minus 0.6. But if you convert this in units of temperature as relevant for long wavelengths, this becomes minus 2.6. And this index is same as the one observed by Arcade or LWA. And this is what makes the accreting primordial black holes an interesting candidates in order to explain the excess radio background. Let me now show my final results. In this figure, on the y-axis I have TR in log scale, and on the x-axis I have the energy in log scale in units of micro electron volts. Uh, for the first result, I am showing a 5% limit of the arcade or LWA limit, which is relevant for the calculation of 21 centimeter modeling in order to explain the HS result. The 5% limit is shown by the dotted line and our result is shown by the solid red line. The gray shaded region in this figure is the frequency band in which the arcade or LWA made their observation. And for reference, I have also shown the horizontal line, black dash line, that shows the CMB temperature at a constant value of 2.73 Kelvin. But keeping aside the edges result, we can even explain the full arcade or LWA limit, which is shown by the blue dotted line, and our corresponding result is shown by the blue solid line. And we can clearly see that we are not only able to explain the magnitude but also the slope of the observation. This is what makes the accreting primordial black holes an interesting candidate in order to explain the excess radio background. Let me now summarize my work. We have looked at the excess radio background observed by Arcade and LWA. We try to explain this excess radio background by the accreting primordial black holes. We find that they are interesting as they not only explain the magnitude but also the slope of the spectrum, that is minus 2.6. As for the 21 centimeter modeling, we find that the excess radio background could be important as this elevates the tension between the theory and the observation made by the edges collaboration. So that is all that I had to say, and thank you for listening.